All right, let's start. So this lecture will be focused on the topic of reinforcement learning. Reinforcement learning is becoming more and more important and popular subfield of machine learning. So I believe it is in general a good idea to start teaching it on all summer schools that we organize. And apparently many ideas and techniques in reinforcement learning can be rediscovered by applying tools that have been known independently in the community of variational inference. So today we will see how it is possible to rediscover those ideas and techniques, exercise a bit in applying variational inference in a bit unusual scenarios, a bit unusual situations, and also hopefully learn a bit about the core ideas of reinforcement learning. So this talk will be organized as follows. So first, I will make a very brief and informal introduction to reinforcement learning. We will also define the most central concept of reinforcement learning, Markov decision process, which is used in almost all research in that field. We will also show that if we formulate this Markov decision process as a probabilistic model and apply variational inference in those models, we will obtain a well-known formulation of reinforcement learning problem, which is called Entropy-regularized. Then we will see how policy gradients and some stable variants of policy gradients can be rediscovered as simply stochastic variational inference in those models. And we will also provide interpretation for the options framework that is used to construct hierarchical policies, hierarchical strategies in reinforcement learning. So before we actually proceed to reinforcement learning, let's consider a few examples of other machine learning problems so that we can contrast RL to other situations and see where there are similarities, where there are differences. So for example, let's take unsupervised learning. In unsupervised learning, we're usually given with a finite sample from some unknown distribution, and our goal is to infer some knowledge about that unknown distribution. An example could be that we are given with a collection of natural images, and our goal is to learn a generative model of similar natural images, and we can approach this problem by fitting a density model to our ground truth data set, such that it maximizes likelihood under our model. And hopefully, if we don't overfit and don't underfit, we both assign high probability mass to the ground truth data, and new sample generated from our model also appear to be from the same distribution as ground truth. So another example is supervised learning. In supervised learning, we're given not just with observations, but also with some target variables that we need to predict. And this can be done again by maximizing likelihood of the target variables given observations. And here, target variable provide us an external learning signal. So this, in some sense, there is a richer information to learn from, although people might disagree. And let's also look at the example of a reinforcement learning problem. Suppose you want to build an agent that will play the Atari breakout game. How would you do that? Well, at each time step, you can look at the screen, at the game screen, receive observations from the game, pass it to your model, decide what action you can take. In this particular example, you have a platform that can move to the left or to the right, and when a ball bounces out of your platform or from a wall and hits a colored brick, you receive a reward. You receive a point. In this game, the reward depends on the color of the brick. But what is important that this process of playing this game is sequential. The rewards you collect are provided you by the environments, by some black box that you can only sample from and not evaluate at any time you want. And your model is simply a policy, a conditional distribution over actions given observations you get from the environment. So your goal here is to maximize rewards that you will receive while playing this game. So what makes reinforcement learning, even on the example of this game or maybe slightly more interesting environments, such an interesting and difficult problem to solve? So first, as it was mentioned, it is a sequential decision-making process, which means that not only that your observations and your predictions are not independent anymore, it can also mean that the decisions you make affect the future decisions you will make and the future rewards, sometimes very far in the future. You might also want to try some actions or sequences of actions, not because you believe they're useful, but because you simply want to gather new experience, because you want to explore and to understand your environment a bit better. So those rewards that you want to maximize can also be very inconvenient. They can behave quite badly. So first, they can be sparse. So you can, for example, receive a reward only in the end of the episode. They can be noisy, and they can be very much delayed. So a good example is you coming to this lecture, for example. So maybe in the year after the summer school, you will apply the knowledge you learned today in your own project, maybe research, maybe industrial project, and you will in the end get a very high reward. You will succeed a lot. But it is very hard to tell whether this will happen today. And once this happens, it will be very hard to associate this high reward with a single decision you made a long time in the past, that you want to apply to the summer school, go to the lectures, don't sleep too much, and so on. And moreover, this high reward can be hidden behind a large number of other rewards that are maybe noisy and don't really mean much. For example, today you had to wake up early, and for example, when I have to wake up too early, I get a strong negative reward immediately. And if I focus only on this instantaneous reward, I will never ever go to any lecture. So I have to overcome this somehow. And this problem with balancing instantaneous rewards and very long-term rewards makes reinforcement learning very hard sometimes. And it naturally defines this problem of credit assignment, that you need to associate the rewards that you receive today with your decisions that you made in the past, so that you can learn and know what behavior is useful, what is not. Another problem with rewards, as we just touched briefly, is this exploration-exploitation trade-off. So whenever you learn something new, you often are not very good at this at the beginning. For example, if you learn roller skating, you may fall very often when you try it for the first time. However, if you want to get from point A to point B, either by walking or by skating, obviously, if you could skate very well, you could go from point A to point B very fast and in much shorter time. However, in the beginning, it is maybe just walking without hurting yourself and other people too much works a bit better. And you always need to balance between acquiring new skills, making trials, receiving instantaneous negative rewards for the longer term benefit, or exploitation, or using the current skills that you have. This problem is absolutely ubiquitous, and it is making many real-world applications of reinforcement learning really hard. So finally, in reinforcement learning, as well as in life in general, we don't always have full information that is required to make the optimal decision. For example, when you're walking in a maze, if you only rely on the observations you get from your environment, from what you see at the moment, and don't remember what have been in the past, where you've been before, well, you can walk for infinitely long time without finding an exit. So partial observability really makes us remember in our past and perform an inference about parts of the world that we don't immediately observe. So the central object in reinforcement learning is Markov decision process. What is it? It is a discrete stochastic control process defined over discrete time, t. We will assume that the time is finite in our case, so it starts from t equals 1 and ends at t equals t big. And at each time step, Markov decision process is in some state st. So what happens next is that our agent that we want to define perceives state of this process and conditioned on that state outputs a distribution over possible actions. These actions we will so for this talk, it doesn't really matter what is the nature of these actions. They can be discrete actions, they can be continuous, or both. But for simplicity, or rather for universality in some sense, for the sake of generality, let's assume they're discrete, because discrete actions apparently are harder to deal with. So once we have this conditional distribution, we choose an action that we want to take by sampling from this distribution. We pass this action to the environment, and in the return, the environment transits into a new state as t+1. This state transition again happens by sampling a state like from a distribution, from a conditional distribution of future state, conditioned on the current state and current action. And this model is likely unknown. This transition model, we don't have access to it usually. We can only sample transitions as we make actions in the Markov decision process, but we don't know this conditional distribution, and we cannot evaluate it in any way. And after we transit into a new state as t+1, we also receive a reward. So reward, we will assume, depends only on the current state and current action. Again, this reward model is unknown to us. We can only receive these rewards from the environment, but we don't know, if we want to know how they're computed, we need to learn this reward model ourselves. And for the purpose of this talk, we will assume that rewards are non-positive. So this is really only a technical requirement. We will see in a few seconds why we need this requirement. But one can also see that if we take a Markov decision process, just arbitrary Markov decision process, and subtract from all rewards at every time step the maximum possible reward in this MDP, we will satisfy this property. All rewards will be non-positive. However, the optimal policy will not change anyhow. So this is only a technical requirement. And in Markov decision process, our goal is to maximize the expected sum of the rewards we collect during the episode as we go from time t=1 to time t=t big. So we want to maximize this in expectation. Since everything is stochastic, our policy is stochastic, state transitions are stochastic, hence rewards are also in some sense stochastic. We want to maximize the sum of rewards in the expectation. And there are different possible formulations for MDPs. So here we're considering episodic or finite time MDPs, where we know that we start at one time and end at some other time. But one can also define an infinite MDPs that would require us somehow discounting returns as they come in the future. But for simplicity, in this talk, we will focus on finite time MDPs, on episodic MDPs. So once we know what are MDPs and what is roughly our goal, we need to, and we would know that we're going to apply variational inference. Let's briefly recap what is variational inference, how to use it. So assume we have a latent variable model in which we have latent variable z distributed according to some prior distribution p of z. We also have observations that are distributed according to a likelihood model p of x given z. And since we don't observe latent variables when we want to measure likelihood of our data, we do this by evaluating marginal likelihood, which is just p of x. This p of x is an integral of a joint distribution p of x and z over z. And for most of the interesting models, this marginal likelihood cannot be computed exactly or analytically. We can only estimate it in some form. And variational inference provides us a tool of estimating this integral from the below. So how do we do that? Well, first we look at the logarithm of the p of x, logarithm of the marginal likelihood. We take into account that this is effectively an integral with respect to an integral or an expectation with respect to p of z. Then we multiply and divide the integrand by some other density q of z. Obviously, this does not change the value of the integral yet. And then we notice that since logarithm is a concave function, and the quantity we want to estimate is logarithm of an expectation, is a concave function of some expectation, we can apply Jensen inequality and get a variational lower bound. So this variational lower bound can be expressed in different forms. They're equivalent, and one of these forms is very will be more convenient for us, which is simply an expectation with respect to q of z of the logarithm of the likelihood minus the regularizer term, minus the KL between q and p of z. So equivalently, we can rewrite this as the original logarithm of the p of x, the marginal likelihood, minus KL from q of z to the true posterior p of z given x. So from the later equation, it is obvious that this bound is a lower bound. It can never be greater than the original marginal likelihood. And the gap between those two is measured by the KL divergence between our approximate posterior q of z and the true posterior p of z given x. The first bound provides a slightly different view. It tells us that we would like to maximize the expected likelihood of an observation under the expectation with respect to q of z. But we will also be punished, we will also be penalized by the deviating from the prior too much. So this object is variational over bound. Hopefully you still remember what it is. We will use it through the talk. So now if we want to apply variational inference, we need a probabilistic model with latent variables. And apparently we can cast Markov decision process as such a probabilistic model. So in this model, we will define a prior over latent variables. Latent variables will be a trajectory, a sequence of states and actions from 1 to t. And effectively, this prior defines a generative process over this trajectory as if it was generated by some prior policy pi 0, if it was allowed to go through the to be evaluated in this MDP. So what is this prior? This P of S1, so we have some prior distribution over the first state where we start. And then at each time step, we sample an action according to policy pi 0. Then we transit to the next state, ST plus 1. And in the very end, we again take the last action. So this is how we generate trajectory using policy pi 0. So once we define prior, we also need to define likelihood. What is likelihood? So we will introduce some dummy variables, R big hat. R big hat is a binary variable that semantically means that we observed a reward at time step t. So if R hat t equals 1, this means that we observe the reward. And since we always observe rewards, even if reward is 0, RT will be always assumed to be equal to 1. And this likelihood will be factorized at each time step and is equal to exponentiated reward we get at the time t. There is also this alpha coefficient, alpha term. Its purpose will be seen a bit later. And here you can notice that since rewards are non-positive, this likelihood is defined correctly and is never greater than 1. And so once we defined our probabilistic model, we need to, if we want to perform variational inference in it, we need to define the family of our approximate posteriors. We need to define the family of Q. And this family so our approximate posterior will very much look like our prior, except that it will be defined using some other policy pi. So in the prior, we use some policy pi 0, our prior policy, and in an approximate posterior, we also generate rollouts, generate trajectories in the MDP, but using a different policy pi, but the same transition model P of ST plus 1 given ST and AT. So we will limit ourselves to this family of approximate posteriors. And so now let's apply variational inference. So we have marginal likelihood, logarithm of P R hat from 1 to t. We know it's a logarithm of an expectation with respect to prior of the likelihood. And let's apply the same trick. So let's multiply and divide this by Q, apply Jensen inequality, and obtain the lower bound. So what we will see in this lower bound? The first term, again, is just an expected likelihood, in our expected logarithm of the likelihood. In our case, this is just weighted sum of the rewards. This is something we would like to optimize in the expectation of all states and actions. And there is also this KL term. This KL term this scale term originally consists of these two distributions. But since the transition model is the same in our prior and our posterior, the transition parts will just cancel out, and only the KL terms between our policies will be left. So at each time step, there is a KL divergence from our behavior policy pi to the prior policy pi 0. And this is the quantity that we will optimize as we do variational inference. So apparently, if we look at this lower bound again, we can see that we can recover entropy-regularized reinforcement learning as a special case. How we can do this? Well, we can look at the KL divergence more closely and see that it consists actually of two terms, of the entropy term, entropy of our behavior policy pi, and the expected logarithm of the pi 0. If we assume then that pi 0, our prior policy, is just a uniform policy, then the last term here will just be some constant that does not depend on the pi, actually, on our behavior policy. And then we will effectively, our lower bound will transform into this convenient and standard objective, the expected sum of the weighted rewards plus the entropy. And this is a very well known and studied object that is often considered in reinforcement learning. So apparently applying variational inference to MDP under certain constraints is equivalent to solving a reinforcement learning problem. So once we have decided what is our objective, what we want to optimize, let's try to find a way how to optimize it. So for that, it is convenient to introduce a few concepts. So the first concept is the value function. Value function effectively is value. So value function is effectively all future rewards we will receive if we start in the state as t. So here it is again weighted sum of the rewards for all time steps starting from time t to time t big, and obviously our KL terms that appear in our lower bound. So one can notice that value of the state 1 is simply the original lower bound we defined. Another function that will be useful to us is state action value. So this is value of the current state, assuming that we're going to take this particular action AT. And again, it can be expressed as instantaneous reward that we get after we take action ST, plus the expected sum of the rewards in the future, expected under our behavior policy pi. And obviously, we can connect these two functions to each other by just expressing one in terms of another. So value function, for example, can be expressed as just as an expected state value function. So we don't know what action we are going to take, so we just compute this expectation, and the KL term that is missing here at the time step t. So now we can derive, we can try to compute these value functions using value functions in the future, at the future time steps. So these are known as backup equations or backup operators. For example, value of state st can be expressed as the expectation of the instantaneous reward and value in the future, value of the expected future state we might transit after taking action AT. And again, the KL term that we receive at the time step t. So similarly, we can obtain a recurrent form of the state action value of Q. So by definition, it is instantaneous reward plus the expected sum of the rewards at future time steps. Obviously, this term is just is nothing else but a state value function computed under the expectation of for future states. And if we want, we can slightly expand this term and obtain an expression that contains Q for the state as t plus 1 and under expectation of action at plus 1. So these formulas allow us to express value at the current state through the value of a future state. And this is convenient for solving MDPs, as we will see in a few minutes. So we might ask ourselves, what happens if we somehow can estimate our value of the current state and action? What policy will maximize estimate of the value computed using estimate of the state action value? So we have this expected QSTAT minus the KL term, and we want to find such P that maximizes this state value. What will it be? Well, apparently the policy that locally optimizes this value estimate is nothing else but a softmax over QSTAT values multiplied by the prior policy. And it can be expressed in this form. So we simply multiply our prior policy by the exponentiated estimate of the QSTAT of the current state and action pair. And we have a log normalizer here that appears to be value of the current state ST. So this PQ will maximize the estimate of the value of current time step. So what is interesting is that if you're familiar with classical formulation of classical non-entropy regularized reinforcement learning, you know that the optimal policy is greedy. The optimal policy is just to pick an action that will give us the best future return. So we just look at the Q values and choose an action that maximizes this Q value. So however, in the entropy regularized case, since value of the state is not just an expected Q function, it also contains this KL term, the optimal policy can no longer be deterministic. It has to be stochastic, because this KL term actually includes an entropy term, as we know. And the solution to this model is no longer a hard maximum of the Q function. It is now a soft maximum of the Q function, which is given by this equation. And if we combine this derivation with the backup equation for the Q function, for the state action function, we can obtain a so-called Bellman equation. So this equation has to be satisfied by the Q function that satisfies this equation is guaranteed to be Q function that corresponds to the globally optimum policy. And this Bellman equation can actually provide us with a contrasting mapping such that it converges to the optimal Q value function. And again, we can see that we can see that it depends only on some estimate of a Q. So Q itself does not have to be does not even have to correspond to any real existing policy. But if we apply this iteration for infinite amount of time, we will have to converge to the optimal Q state value function. And basically, this already is enough to solve MDPs. But the problem is that we can never compute those expectations that we see here. We can never compute them analytically in most interesting cases, because even if we have a discrete action space and we can enumerate all possible actions at time step t+1, we usually have continuous or infinite or some just very large amount of possible states, and it is very hard to compute this expectation. So in practice, people use this equation to derive an objective that they can optimize stochastically. This gives rise to variance of Q-learning. In the entropy-regularized case, it is called soft Q-learning, and this is something we can use to obtain an optimal policy. However, this will not exactly correspond to the inference. So this part is included in this lecture only so that you are familiar with some alternatives to the rest, to how we will perform inference later. So are there any questions at this point? Yes. Can you ask this again in the microphone?
So you told that Q here converges to the soft maximum instead of hard maximum due to KL, right?
So in the traditional Q-learning, what you want to do, at least locally, let's say that you're given with some Q function, and you believe it is correct, it is good, and you ask yourself, okay, if I condition on this Q function, what is my optimal policy? If you don't have any entropy regularizers, the policy that will maximize just this expectation is simply to take the action that achieves maximum of the Q function, right? However, in our case, value of a state consists of two terms, this expectation and the KL term. As we just saw on the previous slides, on one of the previous slides, the KL term is a sum of is effectively, so minus KL term will be a sum of the entropy plus this expected logarithm of the prior policy. It prevents us from collapsing just to a greedy policy, and if you compute maximum of this equation, you will end up with a soft maximum, with a soft max, which is just with a Boltzmann distribution, where the energy is defined by this term and logarithm of the prior policy. So this is how you obtain soft max instead of the pure hard maximum. Any other questions? No questions. Okay, let's take a short break and continue in 5 minutes. Okay, there are questions. But backup, well, I'm not so sure in the etymology of the word backup, but effectively we can, I don't think it matters how you call it. What is important is that you can compute value of a current state using value of the future state. So you can have a recurrent dependency that when combined with the optimal policy can provide you this iterative scheme for optimizing the MDP, for finding the optimal Q function.
Maximizing the elbow has any probabilistic meaning? Is maximizing the variation lower bound that we derived has any probabilistic meaning? Because the probability distribution, or the likelihood that we used seem a bit suited just for this, to derive this particular backup form.
So this is a fair point. It is not clear that our objective, so our objective currently looks a bit artificial, but and we will kind of touch that question whether it makes sense to actually maximize the marginal likelihood. But so far, it allowed us to recover the well-known reinforcement learning formulation of the reinforcement learning problem, and we will see why it is better than some other more familiar forms of solving the problem. So we stopped at the Bellman equations that allow us to compute the Q function corresponding to the optimal policy. And this is nice, and in principle, this is enough to solve MDP, to solve the reinforcement learning problem. But there are a few problems with this approach. So first problem is that even though we have a contractive mapping that is guaranteed to converge to the desired quantity, it is unclear whether policies, actual policies that will be obtained using the intermediate Q functions will be good and suitable. And we kind of solve MDP in a slightly indirect way. So at every time step, it's not that we have a policy and we know that these policies behave in a good way, and we have monotonical improvement guarantees. This is not exactly inference that is the goal of this lecture. So now we will proceed to another way of solving MDPs, that is using stochastic gradient optimization methods. And if we go back and look at our variational overbound, we can kind of remember that it has this form, the weighted sum of the rewards minus KL. And since our goal is to maximize this objective with respect to P, let's just compute a gradient with respect to P. And we will obtain a well-known reinforced gradient estimator. Since our actions are discrete and we cannot evaluate and backpropagate through the transition dynamics, we will have to find such a form of a gradient that allows us only to sample trajectories without actually differentiating through them. And the reinforced estimator for this lower bound will have this form. So here we have a gradient of the logarithm of our policy multiplied by the score, by something that we want to optimize, that by the future objective depending on the action AT. Again, the expected sum of the, sorry, not expected, but just weighted sum of the rewards plus the KL, and gradient of the KL at the current time step. We can backpropagate through, we can differentiate through through the KL at this time step, so it is possible to compute this part analytically. So once we have this gradient that is formulated as an expectation of something, we can obtain a Monte Carlo estimator of this gradient by simply sampling a trajectory from this distribution and substituting it into the whole equation. So if we compute, so since this is an unbiased estimate of the original gradient, using Monte Carlo estimators will also allow us to climb on this function on the variational overbound. And this gradient estimator is very similar to something that is often used in reinforcement learning, which is called, so basically the reinforce algorithm, the original reinforce algorithm, but it's not exactly equal, and we will see why it is not equal. So our gradient has this form with entropy terms in case of the uniform prior policy included in the score, while the traditional policy gradient or the reinforce estimator does not have them does not have the entropy term included as a reward in the future, and also only considers entropy at the current time step. So while this is a good, so while both of the algorithms are known and used, so the traditional policy gradient that does not regularize entropy at the future time steps has less guarantees to converge, and in fact one can construct such a tricky MDPs where only intermediate instantaneous regularization fails to converge at all. And this is a nice inference algorithm because it is model free. As we just discussed, we don't need to know anything about the environment. We can only sample state transitions and rewards, and this is enough to train our policy. And as we discussed, this longer-term entropy regularization encourages us to explore more. We not only care about exploring at this time step, we also want to be in the future states where we explore more. And since we can only sample trajectories from and use this poor score-based gradient estimators, the optimization problem is becoming very, very difficult. And often if you run a policy gradient algorithm on a real task, using different hyperparameters, you will see a plot like this. So on this plot, every curve corresponds to a separate run using a particular set of hyperparameters. And what we can see from this plot. So obviously some hyperparameters are just naturally very bad, so they fail, and this is fine. But some of them are good. Some of them take out quite early and converge to the optimal policy. But there are a few things that makes at least me worry a bit. So some of the runs, as you can see, sort of start climbing on the variational, start climbing on the expected on the expected return. They gather good rewards, but then suddenly something happens and they fail. So this is happening because high variance estimators can sometimes provide us with a bit unfortunate parameter updates that destroy a policy that is already quite good. So this learning algorithm is not very stable. It is not guaranteed that if we that even though we compute unbiased gradient estimates and use them to optimize the function, it is not guaranteed, unfortunately, that in the end we will converge to the global optimum. And very high variance may actually, and bad learning rates, too high learning rates can prevent us from conversion at all. And the question is, can we improve our algorithm somehow to defend ourselves from these kind of situations? Apparently, yes. So now, to see how we can defend ourselves, let's first see, well, what causes the issue. So the issue is caused by the fact that policy can be changed too fast, either by too high learning rate or by high variance of the gradients. So ideally, we would like to improve our policy only just a bit at every time step and make sure we never destroy our policy. So we can only improve it and never make it worse. And apparently, our lower bounds so far already had the solution to this problem. We had this scale term that is doing precisely that. Here, if we assume that pi 0 is a good prior policy, that we don't want to deviate too much, the optimization problem effectively wants us to still maximize the rewards, to improve on the rewards part of the equation, but also make sure that we don't deviate too much from the prior policy. So we are somewhere, so that our policy is somewhere around the prior policy, but is achieving good rewards. And this constraint can be used as to prevent these too fast changes in the policy. And how this can be done? Well, we can imagine like the following EM algorithm. We can initialize pi 0, our prior policy, to some arbitrary distribution. For example, we can consider it to be uniform. And then do the following in a loop. We can take the variational lower bounds, assume that pi 0 is our prior policy, so approximately solve the lower bound, find the policy such that it maximizes rewards, some of the rewards, and minimizes the KL term. And this policy will be a better version of a pi 0. Then we can say that now our prior policy is no longer pi 0, but the pi 1, the one that we just have computed. And then we can repeat this in a loop. Effectively, this is a EM algorithm where we improve our model parameters by first maximizing with respect to Q, with respect to the approximate posterior, and then optimizing the prior parameters using expectation with respect to those posterior. In this particular case, since our prior and posterior share a lot and differ only in the policies that are used in the it can be done by simply substituting or changing policies, prior policy and the policy we currently got as a result of the maximization. And this procedure can be guaranteed to monotonically improve on the expected return. So it should not, unless we set hyperparameters to some completely crazy values, it should not have this bad behavior of unlearning. And recently in the literature, there have been proposed a few other methods that are closely related to this EM algorithm, and they also include some form of KL constraint KL constraining the difference between current policy and the prior policy. So, for example, trust region or proximal policy optimization. They differ only in tiny details, but the idea everywhere is to have the KL term that prevents us from deviating too much from the prior policy. And a natural question to ask is that actually someone asked this during the break is, well, why? So the whole construction looks a bit artificial. So, okay, it is fine that we have a prior of this form and the likelihood of this form, but who said that the approximate posterior has to be factorized in the same way as the prior? Because usually we think that if we have a richer family of approximate posteriors, we can only have better values of the lower bound, and we should not restrict ourselves unless there are serious reasons for that. So what will happen if in this variational lower bound we will use approximate posterior that does not have this form, that is just completely arbitrary distribution as long as we can model it? So there are a few interesting issues that will arise if we don't put this restriction at all. So first, since no longer we have this matching transition dynamics in our prior and our posterior, in the lower bound there will be explicitly this term, logarithm of the transition policy, of the P of st given st plus 1 given st and at. And as it was discussed before, we cannot evaluate this term. We can only sample from the distribution but not evaluate logarithm of it. So it will provide some it will be very tricky and difficult to optimize this bound. You will need to somehow learn a proxy to this transition model. So it is technically not very possible. Second, if we don't restrict ourselves to this form, if our approximate posterior is completely arbitrary, we may achieve unrealistically high rewards. So we can now be able to transit in the states we would never transit otherwise, simply because they provide us such high rewards that they outweigh all other terms in the lower bound. So our agent might start behaving unrealistically, and in general we can find such state transitions that were not even possible under the original model. And the third reason why it might be a bad idea of doing that is because if we could find the exact optimum with respect to Q, if we could find the exact posterior, then as we know the lower bound will effectively result into a just marginal likelihood. There will be no KL gap. And let's look at the marginal likelihood. So marginal likelihood is logarithm of our marginal likelihood of our hat is the expectation over states and actions of the likelihood, which is exponentiated sum of the returns. And if you look at what was the original objective that we wanted to optimize in the MDP, the expected sum of the returns, you will see that these two quantities are not equal at all. In fact, this quantity promotes much more risky behavior because as long as even if most of the trajectories generated by our policy will not result in a high reward, but some of them with small probability will result in a very high reward, this is enough for us under this utility function. While here it will be a suboptimal behavior. So no one said that this utility function makes no sense to optimize. In some situations, you might want to optimize this quantity instead of the standard cumulative sum of the rewards. But it is important to remember what was your original goal, and kind of choose a tool that accordingly to that. So without any constraints, we will effectively be optimizing a slightly different objective. Hopefully, this answers the previously asked question. So, are there any questions so far? No questions. Okay, good. So now we proceed to the hierarchical reinforcement learning. So what is hierarchical reinforcement learning? Suppose that you want to learn a task of roller skating, you yourself as a human. So what is your action space that you have being a human? The only thing that you can really do is to strain or relax muscles of your body. This is how you move, this is how you do everything in the physical world. However, I doubt you think exactly in this form when you learn how to skate. More likely, if the task is to get from point A to point B, you don't think, okay, now I strain this leg, then I relax it, then I strain my back, then I relax it, then I turn there with my torso and so on. You don't think in these terms. In fact, you might not even know that your body consists of such a high number of different muscles. You might not be even aware of them. but you think on a slightly higher level. You think in terms of macro actions. For example, okay, here I want to turn left, there I want to turn right, then I want to gain speed, there I want to brake, there I want to turn around. This is how you plan your journey from point A to point B. As you execute each of these higher level actions, of course, you effectively take lower level actions, but you don't think in these terms. And this motivation, so this motivates the idea of hierarchical reinforcement learning, where the learning and the planning is happening on the higher level than the atomic level provided by the environment. And in fact, this principle is quite ubiquitous. The idea of abstracting away some non-informative details can be seen almost everywhere. In fact, when we do latent variable modeling, usually this is exactly why we introduce latent variables, because we believe that that there are some details that can be details about observations that can be discarded, that are just a result of some noise, and the actual information is contained in the latent variable. So this idea, when applied to Markov decision processes, has the following form. We still have our original MDP, but now policies that we use are conditioned on the options, on so-called higher level actions. These options are managed by a higher level policy that has this form, P of AT given as T and an option from the previous time step. So there is some form of recurrency. And so that we augmented our Markov decision process with some higher level latent variables that ideally should not change the original MDP. And in fact, this trick of providing higher level latent variables such that the original problem is not changed is not unique, and it appears in variational inference in the following form. So again, imagine that we have a latent variable model with latent variable z and observations x, and we introduce auxiliary variables t such that our variational approximation is an integral over t. So we have a prior distribution of qt, and we have a particular approximation that depends on the t, and we marginalize over this auxiliary variable. So a common example for this kind of approximation is if we, for some reason, can only use just normal distributions as our variational approximations, but the posterior we want to approximate is a mixture of normal distributions. Then we can use t to model a mixture of the the distribution. So if t is a discrete variable that is simply indexing mixture components, this marginalization will provide us with a mixture model. And how do we incorporate this into variational inference? Well, we again obtain a lower bound where we integrate over the new variable t, and we augment the original margin likelihood, the original model, with this so-called reverse model. Let's call it q tilde of t given x and z. So one can see that when we fix x and z and integrate over t, this integrates just to 1 because it's a probability distribution. So introducing this term, actually arbitrary distribution over t, does not change the original model anyhow. However, when we apply the same trick with multiplying and dividing with the variational approximation with the q distribution and applying all the Jensen inequalities and obtaining the lower bound, we'll find some additional interesting terms. So as before, we have an expectation of the logarithm of the likelihood. We have the KL term from our variational approximation to the prior, but we also have this additional term that effectively wants us to learn the reverse model, the q tilde, to be a true posterior over t given x and z. And we will see how it is useful in case of hierarchical reinforcement learning soon. So we want to so this is not really crucial, but let's say that our options are again discrete and they somehow enumerate or index our atomic policies. And we want to execute options for some amount of time steps. So we want to introduce a probability Q-continue of continuing a current option if we are in the state ST. So that the higher level policy over options will have this form. With probability Q-continue, we continue the previous policy, and with probability 1 minus Q-continue, we choose a new policy from some distribution. In this form, we can model explicitly that we believe that for for a sequence of steps, we want to stick to the option OT. And the augmented approximate posterior that we have will now have to include some terms for the higher level option policies. So as before, it is a generative process of generating rollouts according to distribution P. So we start with state S1, then we generate our first policy, then at each time step we generate an atomic lower level action AT conditioned on the current option. We transit to the new state of environment, and then we choose the next option that we want to execute. And again, at the final state, we just take the final action. So as before, we need to modify MDP, the probabilistic model corresponding to the MDP, to include this augmented reverse model, the posterior over O over options given states and actions. And we introduce this reverse model. We can, for simplicity, assume that it can be decomposed using just a chain rule, so that we predict each option conditioned on the previously predicted options and all states and actions. But this form is rather arbitrary. One can choose very different forms of reverse models. Something that we only need to choose something that is computationally tractable for us. And the variation lower bound is modified a bit. So now it is again the weighted expected sum of the rewards minus the KL term that prevents our conditioned policy to deviate from deviating too much from the prior policy, and this term. So this term is actually very interesting, and we will see why. So one can rewrite the lower bound in this form. So again, as the KL between marginal policy at time st, where the options are marginalized out, and the prior policy, and this KL term. So this KL term effectively is saying this KL term is very interesting because it prevents us from choosing policies that are not predictable under the reverse model. So if at some time step t, I've chosen an option that cannot be predicted from my future actions that I took and future states I've been in, then probably this option should not be chosen at all. If it's not interpretable, if many different options could be chosen with the same effect, this option is maybe not very, it doesn't make sense to use it anyhow. So this encourages us to learn in options that are interpretable, options that are predictable from future actions and states. At the same time, we can see that without those options, without this term, options are very simple to ignore. Because if we exclude this reverse model, if we don't have this term, then effectively our lower bound is still a valid lower bound, but it's not tight anymore, and it has only this entropy term for options. And one can see that it is very simple to maximize this lower bound by just choosing the maximum entropy distribution over policies and ignoring policies in the higher level policy. So that effectively this lower bound will be equivalent to the lower bounds we worked with before. While otherwise, there is still chance that we will learn some semantically rich interpretable options. And interestingly, in the original options framework, there was no term like this. And there was there was a big there was even a separate and individual issue of learning option discovery, of discovering some higher level actions that are meaningful and useful, while here we have a way of encouraging this automatically simply by applying a well-known technique from variational inference. So basically that's it. And before I finish, I just would like to mention a few things that were not included in this talk because it's just one lecture. That could be of your interest if you're interested in reinforcement learning and how it can be combined with Bayesian methods. So first, there is a topic of uncertainty over parameters, something that we are often interested in Bayesian reasoning. There is this question of exploration. So far, it was addressed very naively by just having these entropy terms in our objective, but entropy is a very weak and simple way of encouraging exploration. There are some much more interesting ways based on Bayesian surprise of things like that. There is also this very interesting trend in the reinforcement learning which is called distributional reinforcement learning, and I believe today we'll have at least a seminar on this topic. I'm sure you will find this very interesting. There is this idea of intrinsic motivation that if our rewards are very sparse, so that it is very hard to learn from such sparse learning signals, we should have some other form of rewards that are maybe intrinsic and not extrinsic. And intrinsic motivation can often be formulated from the Bayesian inference perspective as well. So you might also want to learn a bit on that topic. And hierarchical RL is generally a very big idea, and some people even believe that really difficult tasks cannot be solved by traditional reinforcement learning methods. And since, well, basically Bayesian modeling is all about building hierarchies of latent variables, you might want to learn on other approaches to hierarchical reinforcement learning. So Bayesian reinforcement learning, there is also this idea of Bayesian reinforcement learning. It is not often, so far we addressed, we just use techniques from variational inference, but variational inference is just a very particular tool from the arsenal of Bayesian inference methods, and there are some that can be applied to reinforcement learning as well. You can find some interesting references later in the slides when you download them. So basically that's all. Thank you. Are there any questions?
Thank you for the nice talk. With respect to the optimistic MDP slide that you showed, where you have, maybe you could bring it up on the slides.
Sorry, say this again.
The optimistic MDP.
Yes. So what is the question?
You said that it was sort of overestimating the reward in the future. Is that correct?
So it's not that we are overestimating it. We are just so in the traditional reinforcement learning formulation, our goal is to maximize the expected sum of the rewards. And this optimistic, I wouldn't even call this an MDP, but this construction that we will have if we decide to maximize the marginal likelihood results in a different objective. It's not that we will necessarily overestimate rewards. We will overestimate them if we don't restrict ourselves, don't restrict the form of the approximate posterior here. We can make transitions to some states that give us very high rewards. We can make the probability of this transition to be higher than it is in reality, as long as the reward we will get outweighs, is larger than all other terms included in the lower bound. So it is dangerous. It's like hallucinating, imagining that you're very rich and good, while it's not really the case. So this is the risk with unconstrained.
Isn't that what humans do, though?
Yes, I believe this is what we do very often. The question is, sometimes it's a useful thing, right? We just need to be careful and be aware of the possibility of tricking ourselves.
My main question was sort of, is there a good principled way to sort of increase the risk taking then of agents?
Is that a principled way?
Is there a more principled way to sort of increase the risk taking of agents?
Yes, so basically this quantity is exactly risk encouraging utility function. And if you look at this reference, it effectively provides you with a lower, another variational lower bound, so-called importance weighted variational lower bound, that's very much that is closer to this marginal likelihood in a sense than the lower bound we worked with in this lecture. And effectively, it will, in a principled way, promote the policy you learn to be much more risk-taking. So if this is something you want to do, yes, refer to this paper. Yeah. Any other questions? Okay, then I guess that's it. Thank you.